Okay, this is the last portion of the chapter, is to look at other types of stars besides the ones that were revealed on the HR diagram. There are stars also, by the way, that are not on the HR diagram, just to remind you. Some of the exotic stars, like the neutron stars and the black holes, they don't show up on there, and so as a result of that, we have other ways of thinking about stars too. Well, one of the ways that we can think about the stars is whether they are variable stars. Variable stars would mean that they actually change their brightness. Their luminosity actually changes. The main class of these stars is called Cepheid variables, or Cepheid variables. And the reason why these stars are changing their brightness, and it's really important to understand that this change in brightness is the star itself. The star itself is actually changing its brightness. It's an internal property of the star that causes them to do this. Some stars change their brightness, but not because of anything internally. It has to do with external factors that we're going to talk about in just a moment. So how do they get brighter or dimmer? Well, the main reason why they get brighter and dimmer is because they expand and they contract. So as the star gets larger, you should think to yourself right now, should the star get brighter or dimmer? As the star expands, you would expect that the star should get brighter. The star should become brighter as it expands. Why is that? Bigger surface area. More surface area over which to radiate light, so the star should appear brighter. As the star contracts, there's less surface area over which to radiate the light, and so therefore the star will appear to be dimmer. The stars are literally pulsating in size. There's an instability in the stars that causes them to expand and then kind of overshoot. It's very much like a pendulum. They get too hot in the core, they expand, then they cool as a result of that, but they overshoot. And so then the surface begins to contract, and as it contracts, it overshoots the equilibrium point again, and contracts too much and causes it to get overheated, and then the overheating causes the excess pressure, and that causes it to expand, and it literally oscillates back and forth at a very steady rate, extremely steady rate. And so the typical period of time for these is between about 1 to 50 days. It depends. It's basically dependent on it depends on the mass. What the period is depends on the mass of the star. One of the nice things about the Cepheid variables, and we'll talk about this when we get to the E4 topic, is they're extremely bright. They turn out to be some of the brightest stars, and we can actually see them in other galaxies. That's how bright they are. And so as a result of that, they're very good, very useful as distance markers. We use them in nearby galaxies to figure out the distances to them, because we understand how bright Cepheid variables really are, or at least approximately how bright they really are, and then that therefore allows us to figure out how far away these other galaxies are. Cepheid variable is very important, and again, it's an internal property of these guys. So, for example, if we were looking at a graph of the intensity and then time, what you would see is that they go up and down and up and down. And it turns out that the period of time, right, so this would be big T, the period of time that it takes for them to pulsate one time is dependent on their mass. Because it's dependent on their mass, that means the brightness of the star is dependent on the period. So you can actually use, by figuring out the period, you can figure out its true brightness by comparing it to other Cepheid variables that you've already plotted and that you already know the distance to. So Cepheid variables is really important, and we'll talk about them more when we get to the portion on the galaxies. Besides variable stars, there are also something called binary stars. And technically speaking, a binary star is two or more. Doesn't necessarily specifically mean two stars. It could be two or more. It turns out that in terms of stable situations, that 6 is the maximum number. So what you essentially have is either two stars orbiting each other, or two stars orbiting each other and a third orbiting around them, or the third one might be orbiting around one, and then those two are orbiting around the third. You might have two pairs of stars, and the two orbit around each other. They orbit their partner, and then the pair orbit around the other pair. You could also have 5, which would be 2 and 2, and then one more, maybe out at a much greater distance, orbiting the whole thing. And then lastly, you could have 3 pairs. So 1, 2, 3, and they all orbit a mutual center of gravity. They all orbit around a mutual center of gravity. Now, in our solar system, the center of mass of our solar system is actually physically inside of the sun. So it seems like the planets are going around the sun, but in reality the sun is actually making a small motion as a result of the gravitational pull of the planets. If we look at the Earth and the Moon, the gravitational center of mass for the Earth and the Moon is physically inside of the Earth. So it might seem like the Moon just moves and the Earth just sits there, but in reality the Earth also moves. The Earth is making this little wobble. You can imagine that if you had two equal-sized people and they held arms and they spun around, they would both make the exact same circle. But as one of the people gets much smaller, the smaller person makes a much bigger circle, the bigger person makes a much smaller circle, and if there's a great difference, then you might find that the big person seems almost like they're staying stationary, and then the smaller one is just doing all the moving. But in reality, always both stars make a motion, and how big the motion they make is just dependent on the difference in their two masses. It turns out that more than 60% of the stars that you see in the sky are actually multiple stars, binaries, two or more. And it's not obvious because in most cases the two stars, from our perspective here on the Earth, we are so far from those stars that they appear to be one dot. So it's, as you can imagine, putting two flashlights 50 miles away from each other, they're just going to look like one flashlight. You're not going to be able to see the individuals. Similarly, if you look at your TV looks like a nice continuous picture, but if you were to go up and get close to it and look at the surface of it, you would see it's actually made up of a bunch of little dots. But if you're far enough away, the little dots seem to merge together to become one continuous object. And so this is the problem with most binaries. Most binaries, we cannot see them, and so this creates a little bit of a problem. There are essentially three methods for detecting the binaries, and there are a few binaries that are actually visible to the naked eye. For example, in the handle of the Big Dipper, there are two stars, Alcor and Mizar. They're binary stars, easily visible to the naked eye. As long as you have reasonably decent eyesight, you'd be able to see them. Those are visual binaries. Those are the easiest ones, of course. We can actually see the two stars orbiting around each other. And so I'm giving you an example of what the visual binary looks like. So these two are the binaries. And so here's a picture taken in 1908. We took a picture of the exact same pair of stars in 1915, and you could see that the orientation. You could see how before, if I draw a line between these two stars in the corner, he's well above it, but by 1915 he's almost in between the two stars, and by 1920 he's dropped below that line, passing between the two stars. So it looks like this guy is probably going to make an orbit. So 1908 to 1920, it's about 12 years. Looks like he's made it about a quarter of the way around, so it's about a 50-year orbit, most likely, for these two stars orbiting around each other. Of course, they have the exact same orbital period. They are always on opposite sides of each other. So in this case, we have one big star and one small star. They would always appear to be opposite. As this guy moves over to this point, the other guy would be over to this point. So he moves over to point 3. They always are on opposite sides of the center of mass. The little dot in the center is the center of mass. This is like kind of a different thing than what we think of in our own solar system, because neither one of them seems to be orbiting the other. They're actually orbiting around this point, which is in the middle of nowhere. There's nothing there at that point, and they orbit around that particular point. So that's the visual binary, and what we do is we take pictures over long periods of time, and sometimes we actually notice that the stars are actually moving one around the other. That turns out to be less common than, for example, the spectroscopic binary. The spectroscopic binary means that the stars are too close. We can't see them individually because even in a telescope, the stars appear too close together to be observed. But what we notice is that when we look at the spectra, so maybe we see spectral lines. So we see their spectral lines, and what happens is that since one star is moving towards us and one star is moving away from us, the star that's moving away from us, its spectral lines, so maybe for example these might be the hydrogen lines, its spectral lines are moving towards the red end of the spectrum. So if this is blue and this is red, what we see is that the spectral lines seem to either move right or left, or they may even split. So for example, if the hydrogen lines were present in both stars, then what we would see is that eventually at t equals 1 some unit of time, I don't know how much time that is, the lines actually split because one star is moving away and one star towards. One shifts towards the blue and one shifts towards the red. And what happens is the lines get wider and wider apart. until such time as the stars are, so for example, let me look at it this way. So this is the point at which the one star is moving directly away from us, being red shifted, and the other one is moving exactly towards us, and it's blue shifted. Then at some point, so we started with the stars like this, they're orbiting like this, and so, let me do it this way, and so the star on the right begins to move around like this so that it's moving away from us, and this star comes towards us, and when they're at this point where they're moving exactly towards and away, that's where we're going to see the greatest split. Now as they begin to move around this way, we don't see the red and blue shift. They're not moving away or towards us anymore, and so what we'd expect to see happen is the lines would actually come back together. And they would eventually go back to being one line. Now, one of the things really important to understand is that this is half of an orbit. So we need to actually see the cycle happen twice, and that would mean that the star, so we started up here where they were moving sideways, so we're down here at the bottom. This is our line of sight. We're moving sideways. Now we get around to this point where they're moving one away, one towards us. That's this point right here, T2. Then they begin to move, so now they're not moving directly away from us. They're still a little bit away from us and a little bit towards us. That's T3, and then they move back to this position where they're like this, and they're now moving perpendicular to our line of sight, and so we don't see the red or the blue shift at all anymore. But to make it clear, that was only half of an orbit. The full orbit, we need to see the cycle again. So now the star that was previously over here that was being red shifted as it moved away, now it will shift the lines, and the lines will come towards the blue. Now, one of the things about this is that frequently we don't see this splitting of the lines because, just to remind you, the spectral classes of the two stars are probably different. They probably do not have the same spectral classification, so they don't show the same lines. So essentially what we see is that the line first moves a little to the right, then it moves a little to the left, and then it comes back to the center. So here it's being red shifted, here it's being blue shifted, and then it's back to the center position. And we see this basically going back and forth, back and forth, back and forth. If I were to show you back here on these spectral lines, this is what I'm talking about. I would literally see this line shift a little to the right, and then it would shift a little to the left, and then it would come back, and this would be over time. How much time? It depends. I mean, this could be a period of weeks, months, could be even years. It depends on the star and how fast the orbits are. There are orbits that are hundreds of years, there are orbits that are dozens of years, there are orbits that are literally weeks. The stars are flying around each other. On this spectra, what we would see is, for example, potentially this line would shift a little to the right, it would shift a little to the left. Now, the thing about it is, all the lines would shift a little to the right, and all the lines would shift a little to the left, and then they would go back towards center, and they would just keep doing that back and forth as the stars orbit around each other. And again, that allows us to identify that there is a star there, but just simply that it's too small for us to see with the naked eye, or see them resolved as individual stars. The last type of star is called an eclipsing binary, and this is just by dumb luck. If it happens to be that the two stars are orbiting each other and the plane of their orbit is exactly in line, so the plane of the orbit is exactly in line with the line of sight that we have from the Earth, then what will happen is this one star will pass in front of the other or pass behind it, and we'll see essentially an eclipse. How can we tell that there's an eclipse going on? We look at the intensity of the light. Now, this intensity of light is the combination of the two stars. Remember, they appear to be one star. So this level of intensity represents both stars being visible. But as this star in the front, which is the dimmer of the two stars, passes in front of the primary star, what ends up happening is I now no longer see both stars in their entirety. I see this guy entirely, but I only see part of this star. And because this star is brighter, or this star I should say is hotter, it's releasing more light per unit area than this one is, I see a big dip in the brightness of the star. So this corresponds to 4, where the little star is right in front of the bigger star. And then it moves away and it gets out, and then I see this line go back up. And then for a long period of time, nothing's really happening. This is where we are, I'm going the wrong way. So we're at 5, 6, 7, 8, 5, 6, 7, 8, I still see both stars. But at 9, the dim star passes behind. So now, where previously I was losing the light of the bright star, so I saw the big dip, now I'm losing the light of the dim star, and so I see a little dip like this. And this pattern will repeat over and over and over and over and over again. And basically what we do down here is, this is saying the orbital position, but normally this is time. We just plot the brightness of the star over time, and for some of the stars we notice that they have this little dip, and then they come back up, and this little dip, and they come back up, little dip, and they come back up. And it should not be confused with the Cepheid variable. Let me show both of these two. Actually, I'll just draw it. So for the Cepheid variable, the Cepheid variable is going to look like this. More of that sine wave type motion. So it's real easy to tell whether you have an eclipsing binary or whether you truly have a Cepheid variable. One of the important things is this star is fluctuating in brightness because of an internal property. These guys are fluctuating in brightness because of an external property, because one star is blocking the other. It doesn't have anything to do with the star. Neither one of the stars is getting brighter or dimmer. It's just simply a function of them passing one in front of the other, and it causes this sudden little spike. And then most of the time it's like this. We see this long flat part. The temperature, the brightness or intensity is not changing much. Then little dip, big dip, little dip, and so on. So these are two intensity light curves that both show dips in brightness, but for two totally unrelated reasons.